All right. Hi, everybody, and welcome to today's webinar. My name is Kelly. I work here in marketing at IBWave, and I'll be the host of the webinar. So today's webinar is on LTE surveys, how to do them, what to look for, and how to use the information in your own design projects. Before we get started, I just have a couple of housekeeping items to go through here. The first is that this is being recorded. So we will send out a recording after the webinar. And the second is you should see a chat and a questions box on your screen. So you can go ahead and ask us questions using that as we go through the webinar. Okay, Jamel, if you want to just move the slides forward. Hello. Yeah, and just to the next one. Perfect. So before Jamel gets started, I just wanted to do a brief introduction of our speaker, who is our very own here at IBWave, Jamel Ramal, who is a sales engineer and product owner at IBWave. He has a really long history of experience working in the RF field, designing multiple types of technologies in different types of venues. So lots of experience. You're definitely in good hands here to learn from his knowledge and experience. So with that, Jamel, I'm going to hand it over to you to take over and talk about LTE surveys.
Thank you, Kelly. Hello, everyone, and welcome to this webinar about how to perform a survey for LTE, little comparison with Wi-Fi, what kind of different KPIs we look at and why we look at this one, and what's the difference and what they do tell us, those different KPIs, and how can we troubleshoot if we have the wrong values. And then we're going to go through a demo. So this is the agenda. The KPIs for LTE, how do they compare to Wi-Fi? How to analyze the data we captured when we do an LTE survey, and then how to troubleshoot, some suggestion. And then we're gonna do a live demo. Okay, so let's get started. What are the 5 key important KPI? It's the RSRP, the RSRQ, SINAR, ERFCN, and PCI. So we're going to review each one of them individually. But for me, the 5 most important that we look at when we do a survey is those 5. There are other KPIs, obviously, but those are the most important. And if we compare to Wi-Fi, for example, in Wi-Fi for coverage, we look at RSSI, and usually we look at the minimum of neg 65 dBm. If it's high density venue, we'll generally look higher than that, maybe neg 55 or neg 50. But for LTE, we don't look at RSSI. I'm going to explain why later. We look at RSRP. And for RSRP, the minimum value we usually look at is neg 105 dBm. And if it's a high density venue, we look at neg 95 to neg 90 dBm. In terms of load or traffic, for Wi-Fi, we usually look at the channel utilization, and we try to find channels with the lowest airtime percentage, right? But for LTE, we have a KPI specific for that. It's called RSRQ. And usually we're targeting neg 12 dB or better. Realistically, you have worse than that, but that's the ideal scenario. It's neg 12 or better, or neg 10 if possible. Then you have the noise and interference. In Wi-Fi, there's 2 values for that. There's the SNR, which will show the difference between the noise and the signal received. And usually we want something 25 dB or higher. But there's also the CCI, which is the co-channel interference. And this one, we want the lowest possible, meaning there is the lowest number of APs transmitting in the same channel. However, in LTE, those are combined. So the noise and the interference are calculated in the SINAR. And we want usually more than 10 dB SINAR. Ideally, the higher, the better. Then in terms of channels, so in Wi-Fi, we have just channel numbers. Like for 2.4 gigahertz, we usually want to use non-overlapping channel 1611, so to avoid interference. Obviously, if you're in 2.4, you have to reuse those 3 channels and you end up with having interference, but at least you don't have overlapping interference. In LTE, the channels, they do have like a weird name. It's EARFCN. So if you're doing any LTE survey, remember that one. So in our app, so I'm going to show you later the mobile app, it's just mentioned channel. So you don't have to worry about that, but remember this name. And this is what is the channel for LTE. And this is an example for CBRS, for example. You have like a number with like 5 digits, 55340, and then 56140, depending what channel you're using. And then we're talking about servers, or what device are you connected to? What is serving you the connection, or the connection to the internet, or connection to the network. So usually when you're connected to an AEP, you're looking for the BSS ID of that AEP, right? So you have the ID of that particular access point in Wi-Fi. But in LTE, we have what we call a PCI, which is the ID of your serving cell. So which cell is you're connected to, then you have a PCI. If you want to look for other cells, then you look for the other PCIs. And same goes for the BSS ID. The other BSS ID are for the other APs, even if it's under the same SSID. So let's go to see the first one, which is RSRP. And for RSRP, well, first of all, RSRP means reference signal received power. And by definition, it's the average power of a resource element. And the resource element that is carrying the signal, actually the reference signal, and not any resource element. So in LTE compared to Wi-Fi, so here you see like a graph here with, let's say this is a channel, I don't know, 1.6 megahertz, 1.4 megahertz or something. I didn't put all the resource, all these subcarriers, because there's a lot of them, like I think 72 in 1.4 or something. So I just put few of them to get an idea. So the entire channel, right, doesn't matter what's the width, is divided by subcarriers. And those subcarriers, some of them, they do have what is called the reference signal, which is constantly transmitted at a given interval. And it's transmitted at a given subcarrier, then it's gonna switch to another subcarrier. It's fixed, it's known, it's predefined. And those reference signal transmitted within some of those resource element, in this case, a subcarrier, the device itself only measure the power of that subcarrier, which is called the RSRP. But in Wi-Fi, for example, the RSSI is measuring the entire channel power. And this is equivalent to the total composite power. So in LTE, if you're looking at RSSI, it's the power of the composite, like the sum of all those subcarriers, plus whatever noise, whatever interference. And this is where you end up with a higher value for RSSI compared to RSRP. And if we do the math, the RSSI is the RSRP plus 10 log the number of subcarriers. And the number of subcarriers depend on your bandwidth. So usually for LTE, we like to use the widest possible channel. So for 20 meg channel, you have 1200 subcarriers. You end up with roughly 30 point something dB delta between RSRP and RSSI. So if your RSSI is neg 100, your RSRP, sorry, neg 100, your RSSI is usually neg 70, which is 30 dB difference. So if you're looking for neg 65 RSSI, like in Wi-Fi, then for LTE, you want to look for neg 95 RSRP. And here's just a calculator just to explain to you why it's 30 dB difference. Because the composite power, if you have 12 subcarriers, all transmitting, the composite power, if I'm transmitting all of them at 0 dBm, the composite power is 30.79 something. So that's the total power, everything here, all subcarriers. Even if the subcarriers are not used by, let's say, a small cell, they might be used by another small cell, or they might have some noise in them, or they might have, I don't know how many small cells are around. So the more they are used, the higher the RSSI, and usually it's constantly something like this. So like I said, the target minimum that LTE function like well is neg 105, but if you look in high performance, you want neg 95 to neg 90. So that's, I hope, will explain what's RSRP and why we look at RSRP and not RSSI. And this the RSRP is usually more reliable because it's fixed value. We only measure that one. And the device is actually capable of distinguishing between a reference signal from a given PCI compared to another PCI. Let's say they're transmitting on the same subcarrier, even at the same time, it will be able to identify which one belongs to which. Then we have RSRQ, which is the reference signal receive quality. And this one is a ratio between the power of the reference signal, meaning the RSRP, and the power measured over the entire bandwidth of the resource block. So here I was trying to draw something to explain what is calculated actually. So a resource block has 12 subcarriers. Okay, so if you remember, in 20 megahertz, we have 1200 subcarriers. So technically we have 100 resource block. So one of those resource block will have a reference signal that is measured by the device. Other resource blocks are measured by other devices and so on. And each device will measure its own RSRP based on its location. And when it's measuring the reference signal, it is comparing that power with the power of the other resource element in that resource block. So 2 measurement versus the 12. And the RSSI in this case is measured on those 12. So if I have only 2, like all the resource elements are like free, nothing is transmitting in them, I should have 3 dB delta. So my minimum RSIQ should be neg 3. That's the difference between the delta RSRP divided by RSSI divided by the number of resource block. So the total RSSI of the entire channel divided by the number of resource block will give me the RSSI of only the channel width of one given resource block. And then if I do the ratio with the RSRP, I get what is the difference, how much power I have in the RSSI. So if there are more traffic, meaning there is more resource element used, meaning the RSSI will be higher. If the RSSI is higher, then since the RSRP is fixed, it's not going to change. It's always transmitted here and here. Then the RSRQ will be lower. So low RSRQ indicate high traffic. So neg 3 to neg 10, neg 3 meaning only the reference signal are transmitted. Neg 20 meaning it's jammed. It's all the resource element are used. That's the difference. So usually the RSRQ neg 15 is the highest you would like, would, let's say, accept. But usually what we want is neg 12 or higher, especially for high density. So, and that's obviously planning for more traffic. So that is RSRQ, and we're going to view some examples later about real RSRQ measurement. Then we have SINAR. SINAR is the ratio between the signal and the noise, like SNR, and also the interference. So it's not only taking into consideration the noise, it's taking in consideration the interference. And how LTE is capable of doing that, if Wi-Fi is not, Wi-Fi is just doing SNR, is comparing the signal, the RSSI, with the noise. In Wi-Fi, for example, in 2.4, a lot of interference is non-802.11, right? It's microwave oven, it's whatever, wireless camera, baby monitor, stuff like that you cannot understand. It's just noise. But also Wi-Fi is listen before talk. So if there is something I can understand, then I shouldn't talk, I should wait. In LTE is different. If there is something I can understand, and since it's a licensed spectrum, usually there is not much interference that is non-3GPP. I would evaluate what the other transmitter is transmitting and use other resource element instead of just waiting. If I have a 20 meg channel, I have 1200 subcarriers. I have 100 resource block. I use the resource block that is less used, that has less interference. And this is how the signer is constantly evaluated at the device. The device is receiving the signer, is checking the RSRQ, and then is sending to the antenna or to the transmitter a CQI, which is channel quality indicator, that will tell the cell which modulation to send and stuff like that. And if we have, let's say, two cells using the same channel, inside, let's say, closer to the antenna, you could use all the resource block, for example, here. So let's say this is a resource block, you could use all of them per device. But when you are at the cell edge, then you start getting high interference. Then what happened is that there is something called the intercell interference coordination, or ICIC. And then the resource block are starting being used differently in different frequencies. So in this cell is using the one on the top, this cell is using the one on the bottom, and then they could alternate time slots also. And this is what happens. So in a typical cluster where you have a one channel reuse, so you have, let's say, channel 1, well, in reality it's ERFCN1, but let's just name it channel 1. It's reused 7 times. So you have, for each cell, you might see 6 interferers. And this is where you would need to coordinate when to transmit to avoid interference. But if you need all the resource block for whatever reason, you need maximum throughput, then you use all of them, and each resource block will give you some data, and then your throughput is dependent on your signer. So the signer is calculated RSRP divided by a resource element power. So each a resource block or each resource element. No, you can't calculate each resource element. So you calculate each resource block because you get the RSRP for a resource element. So a reference signal is sent on a resource element, if you remember here. And we calculate the power. This power is the noise and interference. So what is my noise level, the ambient noise? And what is the interference from if anybody else is transmitting in that resource element for that resource block, so that we get the signer. And then usually we want higher than 10 dB. And just since it's not, you might want to compare it with Wi-Fi and say, oh, in Wi-Fi we want 25. Here 10 dB. Remember, if you compare it to 25, you have to account for CCI, which is in 2.4. If you get 3 or 4, you're good. So your throughput is, if they're all transmitting, then it's divided by that number. So what LTE does differently is that it schedules the traffic to avoid that interference, and then each neighboring cell will add interference, so it impact the signer value, so the signer will go down, and it can go down all the way to neg 20. So even on negative values, even if the noise is higher or the interference is higher than, or average interference is higher than my signal, I still can decode at lower modulation. And this interference is non-blocking. I'm not gonna stop and back off because I have interference. If I need a resource block, I will use it. So that's basically signer. Now let's talk about the channels. So sorry, here it's not ERP. Sorry, let me fix that quickly. It's EARFCN. So E-Ultra absolute RF channel number. And those are channel numbers defined by 3GPP, and they correspond to a given frequency, usually in megahertz. They range from 0 to 70,645. Well, that's the last 3GPP specification. Maybe they they will add more channels in the future, but the last time I checked, it was something like this. And then that's for the downlink, and then the uplink, you have from like 18,000 to like 134,000 and 280. Like that. It's just numbers that do not compare to Wi-Fi. There's just so many of them. And one example is that in 3GPP for band 48, there are many channels defined, but if we go to the CBRS and we check the 15 channels that are defined with a 10 megahertz wide, we get those one, the one here highlighted. So you get, for example, the first channel for CBRS is channel 55290, which correspond to the frequency 3555 or 3 gigahertz and 555 megahertz. So that's basically the channel number, and you need that to know which channel are used, which channel I'm connected to, and so on. And we're gonna see some example of why you look at this. Now let's go see the PCI. So the PCI stands for Physical Cell Identity. It's kind of a unique ID. It's not as unique, but it's a unique for a given idea, given area. Sorry. So you shouldn't. It's kind of impossible to see the same PCI on the same channel within the same, let's say, cluster area or the same area where all the small cells are seeing each other. And this number of PCI ranges from 0 to 503. This is how it's defined. So you have 504 possible PCIs within an area. And then when you repeat those PCI, you need to make sure that they are distant. But that's design. So in survey, we look at the PCI to identify the cell. And just for your information, the PCI is calculated using the PSS and SSS. And PSS is the primary synchronization signal, and the SSS is the secondary synchronization signal. And they are used to transmit sequences to identify, so the user can identify the PCI and decode the signal. So the signal is scrambled, and you need those sequences to be able to read and understand which PCI is transmitting what data. So I could differentiate between a data transmitted inside this PCI and a data transmitted within this PCI. And this is kind of an example of different cells. Well, that polygon is like this hexagon is, well, perfect scenario, but we know that it's not going to look like this in real life. But when we do planning, we usually try to see which PCI is where. So here I put like 1, 2, 3, 4, 5, 6, 7. But in reality, you're going to see different numbers. Like there's a random formula to define the different PCI numbers. And then in this scenario, they're using the same channel. So the center of the cell, you could use the entire resources or all the resource block, ideally, or hopefully. And then on the cell edge, you try to use roughly 1/3, because you have 3 interference, or maybe 25% of, if they are all using the channel, then you try to reduce the number of resource block used here. So that's why at the cell edge, not only you get low coverage, like in this picture here. So inside the cell, closer to the cell, you get really good coverage. You get like 4 or 5 bars, and then when you get at the cell edge, you get very low coverage. And not only the RSRP will be low, but also your SINAR will be low, and your RSRQ might also be low. So that's the different KPIs for LTE. Let's go see now how to analyze and troubleshoot the survey data. Here are some examples, and obviously it's way more extensive than that. I'm just trying to give some example on why we look at that and what is it telling us, and what should we do about it. So RSRP usually is an indication of the coverage, right? So if I have low RSRP, meaning I have bad coverage or I'm too far from the server. So this server is the distant server. It does not mean that the coverage where I am is bad. It's just meaning the coverage of the cell I'm connected to is bad. So either the cell is too far, or this cell has a problem. So in this case, if I am, let's say, below an antenna or below a small cell, or I know that the signal should be there, well, I might start by checking that antenna. Maybe it's not connected. Maybe there's an issue. Maybe the small cell is off, and this is why I have bad RSRP. So I'm connected to another one. So those could be different issues, right? It's also possible that this cell is loaded. In this case, I'll go check the RSRQ, right? So if the antenna is good, the small cell is good, it's transmitting, there's no problem, then what is my RSRQ? I go check my RSRQ. If I have low RSRQ, meaning, let's say, I don't know, 18, for example, then the cell is loaded, or it might have high interference, meaning the resource elements are occupied by other cells, and the E node B in LTE, which is the equivalent of an access point, instruct the device to connect to another cell if the RSIQ is too low. There is like some kind of limit, and then if you are below this RSIQ, please use another cell. And that might explain why you are not connected to that specific antenna or specific small cell, because this small cell is just have too much traffic. And in this case, either you check if you have enough capacity to offload the area you are in, or check if there is any interferer, let's say from other cells that are using that they have high traffic, but they are on a different location. And most of the time, just reducing the power might reduce the interference. And I might hear some of you saying, yeah, if you reduce the power everywhere, then your signar also will drop. That's not necessarily true. Why? Because when you reduce the power, then you're taking advantage of the environment. And if I am receiving 10 interferer at maximum power, if I reduce the power, let's say by 3 dB, maybe 1 or 2 interferer will not be visible anymore. They will be below noise. And then their composite power is not taken in consideration anymore when I do my sign-on. And I'm not considering them as interference. They just noise. So they go like drown in the noise. So that's one thing. Smaller area of coverage, low power, meaning less interference. Bigger area of coverage, maximum power. If the cells are close, then you get high interference. So big max power does not mean good. So that's something I learned from my experience doing like stadium designs, for example. Then we need to look at the signar. If it's really about interference or high noise sometimes, then the signar would be bad, obviously. If the signar is bad, then obviously this channel is polluted. So we can check how many neighboring cells have high RSRP. And that's an indication that if I have so many PCIs on the same channel having high RSRP, that explains why I have this bad signar. And I would need to either lower the noise or use like adjust the antenna, especially if it's a directional antenna, adjust the tilt, for example, to kind of reduce the reach of those cells. There are different, let's say, interference mitigation, but if it's not something coming from neighboring cell, then in this case, it might be something external. It might be any noise, either generated. Most use case scenario, it could be just a PIM generated, especially if you're doing DAS. It could be like a product of intermodulation, just two frequency mixed into the DAS, and then there's some bad connector somewhere generating an interference in a third intermode, and then you see it in that particular channel, and it might make your signar bad. So that's some troubleshooting you need to do. Otherwise, it could be something external. It could happen. I've seen that in the past, and then in this case, you would need a spectrum analyzer and track it down and just remove it. Since it's licensed spectrum, it's not like in Wi-Fi when you have interference from non-recognized device, or well, unless they are in your own, let's say, control, your environment, your network, you might be able to shut them down. But in public space, you can't do anything about them, right? It's just it's an unlicensed spectrum. But in LTE, most of the time, well, almost all the time, it's a licensed spectrum. So you just call the regulators, and then they're going to shut down this interference. Now, channel number. So if you're looking for a specific ARFCN, because whatever, you installed a new network with, or a new small cell, and you're using new channel, let's say CBRS, and then you want to check the different channels that are transmitted the location as designed, right? And you may notice you're not connected to the expected covering channel, right? So you design for channel whatever X, and then you're seeing you're connected to channel Y. And this could be due to everything we talked above. Problem with the coverage, cell already loaded, bad signer, so you move to another cell, and this other cell is not on another PCI, it's on another channel. And this case, you need to check your channel reselection parameters. If everything is good, I have good coverage, I have good RSRQ, good signer, it's just when I'm in the area where this channel is supposed to be covering, I can't connect to it, then maybe your channel reselection, meaning how the E node B or the small cell is instructing the device to change channel based on priority. So this channel is number 1, this channel is number 2, this channel is number 3. So in this case, maybe the area you are in have another channel with better parameters, a channel with better RSRP, better RSRQ, and this is why your device is connected to that channel. It may be nothing wrong with it, it's just the other one is better, that's it. So this is why you need to check, and then with those channel reselection parameters, you define which one is the priority to connect to, and then you can define, you may understand why it's connecting to that one. And same thing if it's the PCI. Let's say if it's a DOS, for example, you expect to see the same PCI everywhere, right? You don't want to see any PCI from outdoor. And if it's small cell, you want to see the PCI when you are below or closer to that small cell. And if not, then same thing here. Well, we check everything above. Maybe it's bad coverage, maybe bad RSIQ, maybe bad signer, maybe the channel reselection is telling me to go to another channel as priority, and this other channel does not have this PCI. But if everything is okay, then you check your mobility parameters, meaning maybe your mobility parameters are too strict. Let's say I consider my RSRP good, but the RxLev min, or the minimum signal to connect to that cell, is high, is whatever, neg 90, and I'm seeing neg 95, and this is why I'm not connected. Maybe the RSRQ minimum was too high. Maybe it was set neg 12, I'm seeing neg 13, neg 14. I think it's okay, but it's not. The cell is telling me, go check for another PCI. And same thing for signer, and same thing for channel, go check another channel. So that's some example. Obviously, we can't summarize everything, but it's just to give you a snapshot. So that's the theory, right? We've seen the different, well, the major KPIs I think are the most relevant in LTE. And what we can do now is go and have a demo. But before that, maybe we can see if there's any questions, or we could maybe answer them. Kelly, do you want to see if there's any questions?
Yeah, there is a few here. Let me just pull out a couple. So in terms of this compared to 5G, are the KPIs the same when you're talking about 5G, or would they be different?
5G, it's going to be most likely the same. Well, most of them are, well, they are the same technically. It's just, you might see something like SS RSRP instead of RSRP, and you see SS RSRQ instead of RSRQ, but it's pretty much the same in terms of KPIs. It's just there's more of them. There's like SS RSRP and then CSI RSRP, but usually we look at SS RSRP. We might do something similar in the future once we have 5G supported and talk about actually 5G surveys.
Okay. And there's one here specific to stadiums. For venues like stadiums where we implement multi-sector LTE on the seats, what is your recommendation to improve the SNIR and keep the SNIR 10 dB or above?
So for stadium, and I'm speaking by experience, I've done stadiums in the past, and one of the things I've tried, and I'm not sure if it was tried elsewhere, and if you tried this, is to do channel interleaving. So instead of putting all the channels in the same sector and covering a seat section, and having the cell edge between the two sectors having really bad SINR, and having like half the seat section is polluted from the cell or the sector on the right, and the other half from the sector on the left, why not using different channels? Let's say use band 4 and band 7 and band 2, and then interleave them like it's done in Wi-Fi. In Wi-Fi, for 2.4 is channel 1, 6, and 11, and then you try to do like channel reuse, but with interleaving. And I might hear you talking about carrier aggregation, where you want, let's say, all the 3 channels to have carrier aggregation. You can still have this carrier aggregation by not polluting, but by leaking the next channel on to the right and to the left with just the side lobe, to have half the seat section with one channel, the other half with a second channel from one side, and then the other half with another channel from the other side, and you end up with some carrier aggregation. Anyway, the sign-on would be too bad if you put everything together, that sometimes the carrier aggregation will not work anyway.
Okay, great. So actually I'm gonna, there's a couple of questions here on what survey tools do you use and how can you get these KPIs on an Android phone, which I think sets up the next section of this webinar quite nicely. There are more questions, but in the interest of time here, just to make sure we kind of get through all of the content, why don't we move on to the demo, and then we'll get to the rest of the questions as best we can after this point.
Cool. Okay, so I'm gonna show you our mobile survey app, and that's one of the tools you could use to do LTE survey. And why we use that one? Okay, so this is my tablet. It's an Android tablet, and that's the tool is iWave Mobile Survey. I'm using the latest one, 16.1. It's still in beta version, so I'll try to show you some new stuff. And this tool, well, first of all, it will remove the need for a hardware, right? So usually if you want to do an LTE survey, traditionally you would use a scanner, right? Or you may want to use a device that is rooted and have like a specific software and a specific customized OS, I mean, to get like some specific other deep level detail, like level 2 and level 3 messaging, stuff like that. But here is what's cool with the fact that we could use Android, is that the Android API allow us to capture those key KPIs, and we could see them from the point of view of a device, and we could use any Android device usually, ideally Android 10 or higher. And so far Samsung device work best. I'm not doing any advertising for Samsung, but it's just the devices we tested, Samsung worked best. And most people already have a device like this, so you don't need to purchase any hardware. And honestly, I have tablets, the Galaxy Tab A. It's a cellular tablet, can work. It costs like $300 tax in. So that's why we use that one. So I'm going to show you an example. So when you launch the app, you see the list of project, and then you could create a new project or open from server, or just look your project on the cloud, start from a template. So if there is an existing project, the design was done, then you could download it from the server and do a survey. In this case, let's say if I start a new project, and let's say I name it demo here, and then I create that project, then I have the option to create the floor plans. And I could have an outdoor plan if, let's say, I want to do, let's say, the parking lot or whatever. If it's, let's say, a campus, I have different buildings, then I could have multiple buildings and then the outdoor view. And then for each building, I create a floor plan. And then the floor plan, I could take a picture or select a picture or just sketch up something from scratch. So most use case scenario, you go to a building, you find the floor plan of the fire exit or something, right? So fire exit plan, for example, or a floor plan that's printed somewhere. So let me do this scenario. So let's say here, it's turning. I take this floor plan, for example, I printed, and then I can crop it, right? And then use it. Now what I need to do is to scale it. Oh, what happened here? So I just need to move the scale here. And then this is, I believe, 90 meter. Then here's my scale. Then I have other options to add push pin, to document where's the equipment room, to add some markup, to draw some walls or something, to define the cable routes. That's kind of side documentation, right? But here we're only concerned about the survey. So before I start the survey, I'm going to define an interpolation area where I want my survey heat map to be generated. So this is simple, it's just a rectangle, but it could be a more complex venue, right? With like some shapes and stuff like that. And then I have the plus, the add the new survey here. And I click add, and I have the option to actually do cellular, Wi-Fi, or both, and I have a stop and go and continuous. So stop and go is really when I want, let's say, accurate and precise location of my survey. So let's say I want the measurement to be taken just below the antenna, and then, I don't know, 10 feet from the antenna, then 20 feet and something. So I do stop and go because it's going to be only taking measurement where I want the measurement to be taken. And then continuous is basically a straight line. It will spread the point between the first and the second one. Ideally, you don't go too fast, and then you try to click often, because if you walk in a long distance and then the next click, the point are spread, and the accuracy or the precision of the location are not good. So ideally every 3-5 step you click, but that's depend how fast you want to go. You could give it a name. In this case, we want to do, let's say, Wi-Fi and cellular both, and we create. So when we create, we could start walking. Let's say I am here, the lobby entering, and I'm walking, and then I go here, I click again, and then we have like a network monitor here that's telling me what's the access point I'm connected to in 5 gigahertz, all the access points available, and then the 2.4, and then I'm seeing the LTE cell I'm connected to. And in the meantime, I was walking, let's say all the way here, and so on. And you see the points are spread, but they are not equidistant, because some of them are Wi-Fi, some are LTE. If you're doing Wi-Fi only or LTE only, you see the exact same distance because it's the same scan tool. And then I keep walking till I finish my floor plan. At any given moment, I can pause, go back, let's say add a push pin. I need to take a picture of something, I notice something, and then go here and then resume my survey, and it will resume whatever I left. And when I'm done with my survey, I just click done, and then it will finalize the data, and it will run the interpolation by default. So that's the heat map generated based on the data. So this is 2.4. It's capturing SSID, the different channels, and I have RSSI or CCI. And then for LTE, what you noticed here is that we have 4 different combination of band and technologies. So we have one HSPA or 3G on the 850 band. We have 2100 LTE, and we have 850 again, but this time is LTE, and we have 1900 LTE. So this is what my phone was capable of seeing. So this feature was only possible to do with a scanner, where you could scan multiple channels and multiple PCIs for multiple carriers. Using Android, obviously it's limiting to one carrier because it's depending on what SIM card they have, but I could see what's my 1900, and I could go look for my RSRP, and this is my RSRP. Obviously I was static on one location, so my RSRP is somewhere neg 100, and I could see the list of channels. Obviously is one channel here, and then the list of PCIs. So I know that there is 3 PCIs. So one is serving, and 2 are interferer. And if I click on any given point, I would see the data. So the band is band 2 for LTE 1900. The band name is PCS. I'm connected to Rogers. This is the cell ID. This is the PCI for 51. RSSI, RSRP, RSRQ. In this case, SINAR was not collected because it's not the serving cell. And you see the S here is telling me the serving cell is actually on 2100, and it's the PCI 435. So I need to go to 2100 to look for that one. Then if I go back, I filter 2100, and then I filter by 435. That's my serving cell, and that's the coverage I have for that serving cell. If I click here, same point, now I see my serving cell, and now I see the SINAR captured. And you see the downlink channel, the uplink channel, the channel bandwidth, some device reported, some not, and same thing for CQI, some device reported, some not. And you see, since it was my serving cell, I had more information. I had the inland BID, and I had MCC, MNC, and the TAC. Obviously, those repeat within the network, so it's not a problem. But the SINAR is really calculated if you're connected to that cell. And then what I could see is what are the interferer. I have 2 other servers. So I have 2 other servers, and my SINAR is kind of bad, and my RSRQ is also kind of at the limit. And I could see the power of those 2 servers, and I could see their RSRQ. So that's the RSRP map, and I could filter and see the RSRQ. And here it was NEC 15, here it was NEC 13. So you see it's fluctuating based on the traffic. Also see my RSSI between NEC 60 and NEC 65, and I could see also my SINAR, which was fluctuating between 2 and 8. So that's the different KPIs I could see. Now let's go check a complete project I did. So this is our office at iWave here in Montreal, and I went there and I did the entire floor. Let me just zoom out here, and I captured as much data as I could. And here we have a DAS, and the DAS is actually connected to 2100. So here you see I have 5 different LTE bands and another 3G band plus the Wi-Fi. And for each band, I'm capturing all the PCI. So it's a lot of information that I could use to evaluate the coverage. So our interest was the 2100. The DAS was supposed to repeat that band. The channel was supposed to be 2050, and then the PCI was supposed to be 262. So if I do PCI 262 and I do interpolation, that's the coverage. And just by seeing the heat map, it's kind of jump into your eyes, the blue area here. So here we're using, let's say, rainbow heat map colors. And the blue area here is where I have concern. So anything that's red, orange means hot, it's good. Anything green, it's still okay. Anything blue means it's cold. You see it's lower than neg 105, we're in neg 115. What this is telling me for the RSRP is my DAS antenna here is not working, or maybe my remote is not working, it's turned off. So I need to go troubleshoot this area here. It's kind of, it's easy to jump into your eyes. And I could also define a compliance. You see here it's failing 84% because I was looking for neg 100 90% of the time. But this is not what I'm getting, right? I'm getting lower than that. So that's basically what you could see. If I switch to RSRQ, it will also tell me this area here, it's really bad. So the RSRQ is kind of neg 20 here. And if I go to the SINAR, I would see my SINAR was not collected everywhere, but when it was collected, it was bad. So even my DAS, it's kind of polluted, right? Because it's just retransmitting something from outdoor, indoor, even if the coverage is good, well, the SINAR might not. And you see sometimes it was not the serving cell actually. In this area, I might be connected to something outdoor that is better. And in this case, it was 1900. So we'd need to kind of, it was 2.6, I believe. Yeah, this area was 2.6. So you see in this area, 2.6 was better than 2100. So I would need to contact the carrier and see if we could add the 2.6, since this one seems to be dominant, almost 1/3 of the floor plan or more, then that's what we need. And one last thing is that once I'm done with my survey, I could actually generate a report. So I could go here, click on the PDF, and then I want my survey map, and then I could select, okay, which band I want to include, which technology, and then which KPIs. I want RSSI, RSRP, RSRQ, SINAR. Maybe I'm not interested in RSSI. I'm not interested in HSPA, so I just want LTE, and I'm not interested in Wi-Fi for now. So I'm just gonna run a report to have the LTE and the difference. So I could add maybe title page and run that. So I save it, and it will generate a PDF report with all the channels on all. Well, I have one floor, but if I had multiple floors, it will select all the floors. So that's basically what is done with the survey. And once you complete your survey, complete your analysis, you could actually save that to the cloud or to Unity, and then you could open it in design. So this is my RSRP map for 2.6, and then RSIQ for 2.6, and then my SINAR for 2.6, and so on. And then the other band, RSRP, RSIQ, and SINAR. So this will conclude our demo. And we invite you to download a free trial by going to ibwave.com/mobile survey, or just scanning this QR code, so you could play with it with the tool if you have an Android device. And we have a few minutes left, so we could take one or two more questions.
Yeah, we got quite a lot of questions as we're going through there, Jamal. Good job, thank you. For any questions we don't get to, we'll do a follow-up with you afterwards to try to get your answers. But a lot of questions around a couple of topics. One is around how to capture more than one carrier during the same survey. So does it do kind of multi-carrier?
For now, no. We started with one carrier, so your phone has one SIM card, one carrier. We're planning to add to support dual SIM card devices, so you would be able to do 2 carriers. And then in the future, we plan to also add multi-carrier, where you would be able to connect multiple devices via Bluetooth to, let's say, a master device. In this case, you would be able to capture different carriers at a time.
Okay. And will this capture 5G NR data now or in the future?
For now, no, but we're planning to add that soon.
Okay. And I guess just a point of clarification, people are asking about the scanner that's needed for this. So maybe you can just clarify, there is no scanner needed for this, but it is optional that we do integrate to others. So maybe you can just give a brief clarification on that, Jamal.
Yeah, so the scanner is not needed. This demo was done purely using the tablet, the Android tablet, no scanner connected. It's the Android API returning those KPIs, returning all those PCIs, all those channels, and the RSRP, RSIQ, and SINAR. We didn't use any scanner. I do have a project with the same project with the scanner, and it's pretty much the same channels, well, the same bands, more channels because I have the channels for the other carriers. And then I have the KPIs everywhere, not only when I connect it. For example, the SINAR, I could see it everywhere, and not only when I'm connected to the cell. That's one of the difference. But no, we didn't use any scanner in this demo. It was live. It was only my tablet. I don't have any scanner with me right now. And you saw I didn't connect to any third-party tool. But if you need a scanner, there is like a share button. Let me show you here. So if I go back to survey, I have a share here. If I click share, it will share the IBWC. That's the format we communicate with apps that do that actually connect to a scanner, like PCTEL or Nemo or Solitelia, or there are so many of them, or Roden Schwartz solution. We have a list of compatible devices.
Okay, great. So we're just over time. So unfortunately, we're gonna have to end the webinar there. Apologies to the questions we didn't get to, but again, we'll do our best to follow up with you. and get you answers. Feel free again to download your free trial, either through that QR code or the link, and we look forward to hearing any feedback you have. We hope you enjoyed the webinar. Thanks very much for joining us.
Thank you, guys, and please connect on LinkedIn or Twitter. If you have any question, you can contact me. No problem. I'll try to answer. If I don't know, I'll find the answer. Thank you.
Thanks, Jamal.
Bye-bye.